for international collaboration within this quantum research education infrastructure. So first speaker of this session is Mr. CHAO Tsu Yu from Industrial Technology Research Institute from Taiwan, and his title talk is Quantum Technology and International Collaboration Strategy from Taiwan's Perspective.
Hello everyone. Finally, it's the last section. Right, it's a long day. Hello, my name is CHAO Tsu Yu, and I come from ITRI, Industrial Technology Research Institute in Taiwan. We call ITRI. We are the non-profit research institute in Taiwan. I think most of us or many people know Taiwan because of TSMC. Actually, TSMC was spin-off from ITRI at 1987. So I think that's my talk regarding quantum technology collaboration strategy, especially at the year of the quantum technology. So let me take a very short introduction regarding my organization. I think ITRI, we are the organization. We don't do very fundamental study or research. We are the main mission of ITRI. We are closing the gap between technology and industrialization. Right now we have total staff over 6,000 full-time employees, and if we include a subcontractor, we are over 8,000 employees right now. We have branch office all around the world, including in San Jose, in Tokyo, in Berlin, in London, and Bangkok last few years. I think most important of all that we have over 28,000 alumni of ITRI, because that even the founder of TSMC, Morris Chang, is our former president of ITRI. There are many ways that ITRI engage with the industry. The first of all is that the technology transfer to Taiwan industry. The second is spin-off, like TSMC or other many cases that we spin off from ITRI. Right now we have more than 166 startups spin off from ITRI, and among them we have 43 exist for IPOs. Right now, for now, we have more than 1,000 billion US dollars for market value from our IPOs. We all know that TSMC, not only TSMC, including UMC, Vanguard, etc., is also spin off from ITRI. So right now we have many research areas, not only in semiconductor, but also in information and communication, like low orbit communication, 6G, electronics and Apple electronic system, material and chemical, etc. So we are a very big and comprehensive research institute in Taiwan. So let's jump into the quantum technology. So from ITRI point of view, the first question is that what quantum technology will bring us? Because ITRI, we are a funding organization from the Ministry of Economic Affairs. They will ask, our first question is that where is the market and where is the industry? So that's the first question we each ask ourselves. So let's back to the history. We saw that electronic computing bring out the like a transistor and semiconductor, and internet bring out the personal computing. So we are thinking about what industry or what impact from the consumer or from the market point of view that quantum technology will bring us. So I would like to give some numbers that there are two point of view. One is from the market size or market forecast point of view, that a lot of numbers figure out that quantum technology or quantum related market will be very significant in a few years. The other hand is that over 30 countries put quantum as the national strategy because of quantum technology can be the national security issues. So I think that's the very key questions. I think not only from Taiwan point of view, and I think many of us will agree that quantum technology will play a very important view in the near future. So what's the Taiwan status regarding quantum technology? So like this morning, Dr. Bao said that Quantum Taiwan program, or we call Quantum Taiwan Initiative, that's the first initiative or giant program in Taiwan. From the 2021, we collectively invite 17 members or teams to join this program, including industry, academia, and research institute. The main focus is that from the first day, we see the quantum technology should be an ecosystem, not only in university or academia research. So from the 2021 to 2025, more than I think 0.3 billion US dollars invest in Taiwan, including quantum computer prototyping, quantum communication, and next year we will launch the Phase 2 Quantum Taiwan program. So from the academic point of view, academia Silica is the core of our Quantum Taiwan team. They built the 5-qubit superconducting quantum computer in 2024. I think the number of qubits is not that important from our point of view. We are building the platform for the chip fabrication and testing, and looking for the modules or subsystems opportunity to collaborate with Taiwan local industry or international partners. I think that's our first strategy. The second is that from the Taiwan industry point of view, I think I would like to give 3 examples from Taiwan industry point of view. First is the world's biggest EMS company, Foxconn, in Taiwan. They established trap ion lab and control system infrastructure in Foxconn. They build up a lab, collaborate with, I think, strongly with Australia experts. The number two is that quantum computer is the world #1 AI server manufacturer, I think not only in Taiwan, globally. They invest in two kinds of quantum technology, leading startups, including Rigetti and Continuum. From their point of view, that at this moment, they want to know which quantum technology will win, or maybe two technology will both exist. So the quantum computer invests two kinds of technology at the same time. The third is the control electronics. They are the biggest personal computer or laptop manufacturer in Taiwan and globally. They invest in GPU annealing, technology for AI-driven precision medicine research. So I think let me use these three kinds of cases to demonstrate that from Taiwan industry point of view, they are still looking for future opportunity or the position of Taiwan industry. The third is that research institute. In Taiwan, we have a National Lab for High Computing Center. They would like to combine with HPC and quantum computer. That's the main goal of our Taiwan quantum program, phase 2. And what E3 do is what we do in E3 regarding quantum technology. We have two teams to do the quantum technology. First of all is that we design the low temperature superconducting quantum hardware, especially combined with the TSMC process. Doing so that we can reduce the overall module system downsize to over 40% and reduce the power consumption. I think why we think about that, because that right now the chamber is very big. It's very hard to reduce or replicate or industrialize that kind of instrument. The other team is that enabling users to access the hardware from the software side, because we think about when a lot of users wants to use the quantum computer or quantum technology, they have to user-friendly environment. So talking about collaboration, because Taiwan is a very small island, and talking about quantum, we are not the leading country in the world. So I think collaboration will be very important from Taiwan point of view. First of all, I think prototyping and industrialization will be the first issue. So we are thinking about three ways. First of all, that quantum hybrid computing platform. We are talking about how to integrate with quantum computer and supercomputer. We think in the future, this kind of two computing resources will emerge and combine. The second is that quantum subsystems. I think from Taiwan point of view, that a lot of business or industrialization should be standardization and industrialization. So just like mainframe to personal computer, the standardization is very important, and how to do the cost-effective components or subsystems. The second is that application innovation. So in Taiwan, we have few quantum application use cases in Taiwan, including the chemical and medical drugs discovery. So I think we have three strategies regarding application innovation. First of all is that integrate quantum algorithm with AI. That's the first strategy. We want to collaborate with international partners. The second is that QKD cybersecurity, especially in Taiwan, we have prototyping regarding quantum communication pilot line in Taiwan. So we want to collaborate with international partners. Three is that simulation and optimization, because that in many application innovations should be very important from the simulation and optimization. The last is that standard and the alliance for commercialization. From our point of view, that quantum standard will play a very important role for industrialization and commercialization. Even though that Taiwan is not an official member of ISO, but I think Taiwan is very eager to join every kinds of standard activities. We want to join this kind of standards and come to Taiwan and collaborate with partners to commercialize or industrialize this kind of technology. The other thing is that quantum alliance. Just as I said that in Taiwan we have a Quantum Taiwan project. It's the kind of quantum alliance. But I think from the global point of view, quantum alliance is very important, because that even today a lot of technology should be solved in the future, but I think only account one company or one country should not be the right solutions. So let me go to the conclusion. I think Taiwan, just as I said, that Taiwan is a very small island, but we have a very strong manufacturing, especially on the semiconductor, ICT technology. You can find very kinds of solutions just around the corner. You just play ping pong, just Professor said yesterday, or just play basketball. Basketball, you can find your partners or vendors in one place. So I think that's why Taiwan matters, not only in semiconductor, ICT. I think in the future, in quantum era, I think Taiwan can be a very good partner for you. So I think, I would like to use this kind of place to invite all of you to come to Taiwan and come to E3, and looking forward to have more opportunity to work with you. Thank you.
Okay, so thank you very much for the nice talk. This presentation is now open for discussion. Any question? If not, then I have a question. ITRI is not only creating the environment for researchers, but also actually aiming for some industrialization, commercializations. Does that mean also do you use, for example, invest, which can be in return for commercially as well?
No. Our sponsor, mainly from the government. Over 70% of our income from the government, other 30% is from industry. So we are not a revenue-oriented institute. When we have revenue, so we invest in the future to buy more facility, to do more R&D activities in each.
still you collect revenue from
Yes,
from
yes,
your
yes, yes.
I was wondering if E-Tree is involved with designing chips for decoders for quantum error correction. Not yet.
But there's a lot of startup group of photography.
Yes.
So that's possible. So I think that they are developing that.
Oh,
그게 되면 벌써 이 브레인 드레인, 이 where trained PhD goes to Europe or United States. There's similar program
we don't have that solid program with universities, but I think we have many projects collaborate with the university, and university professors send their students as the intern or the learning in their summer period to E-Tree.
I think the question was the brain drain. So if you educate your quantum workforces and
Okay.
was it they go to abroad?
Sure. I think first of all that our talent from the Taiwan academic university. The second is that we send out some our engineers into the I think maybe Europe and the US to learn their technology.
But it was saying about the brain drain, meaning like, do you have any way to keep your workforces trained in Taiwan, eventually work in Taiwan?
No, we don't get enforcement to keep the talent just only for Taiwan company.
He told me that they go to TSS.
Okay. So brain to TSMCs.
Yeah.
Okay. So any more question? Then let's take the speaker again, and then let's move on to the next presentation.
Thank you.
Okay. So next presentation is from Yong-Soo Kim from Korea Institute of Science and Technology. He's gonna talk about bridging discrete and continuous variable quantum optics. Joint research across Korea, Singapore, and Australia.
Thank you for kind introduction. My name is Yong-Soo Kim from KIST Center for Quantum Technology. So today I'm going to talk about our international collaboration research project among Korea, Singapore, and Australia about the discrete variable, continuous variable quantum optics. So we had a very interesting talks about the national agenda of quantum science and technology, but my talk will be more, small scale in terms of so I will particularly introduce our ongoing research project among those three countries. So before I begin to introduce our study or researches, I would like to introduce what KIST is. So KIST stands for Korea Institute of Science and Technology, and which is a government-funded research institute, which means that it's not a university. However, many of us are actually co-affiliated with the university, including myself. So we have also postdocs and students in our campus. Actually, we have more students than just regular researchers as well. So actually, it's in Seoul. So it's in Seoul, 30 minutes from the CBD area. And as for collaboration, I would like to emphasize that we have really great, affordable, economical design awarded guest house. So it was awarded in 2000, about 10 years ago. This was awarded, some design award or whatever. So you can actually, if you visit the KIST or Seoul, you can stay here very comfortably. So if you see the map of Seoul, so this is the map of Seoul, and you can see the Hangang River there. And KIST is located in the north and east part of Seoul. So from KIST, you can go to a CBD area via metro in 30 minutes. And also, if you still remember a quite old song from Gangnam Style, the Gangnam area is also about 50, less than 1 hour. So it's a great location to stay. Also, I would like to also emphasize that with only 30 minutes by metro, you can go to a Bukhansan Bukhansan Mountain National Park, which also we often to have a large, huge snow during the winter time. So for those who are from those countries which doesn't have any snow, you are welcome to visit us and stay during winter time, by the way, except the winter is coming. So to introduce our Center for Quantum Technology, actually we begin our Center for Quantum Information in 2012, and I myself joined the center in 2013. And last year we have launched a Center for Quantum Technology to cover some so-called quantum engineering technology. So our research center, we have a 24 principal investigators with 20s or postdocs and more than 100 students. And we actually define our work as a quantum contents, which means what to implement, like a quantum, some fundamentals with quantum studies, and also how to implement like quantum engineering and where to use it, so quantum applications. I myself name as a so of course that just you cannot really distinguish one from who is going to belong to where. However, that I define myself as a quantum contents or some fundamental researchers there. And if I say in KIST we are doing contents to implement in engineering to application, which means that we are doing everything from the very beginning to application, right? And it may mean that we are doing nothing. However, it's not because that just we cannot really couple with other physical platforms. However, just we only do a quantum optical platforms as well as deep learning solves. And I'm doing some optics, as you can notice from my title of my talk here. So photonic qubits. So for the photonic quantum information research in KIST, just we do several projects, and we are doing some several projects. However, we want to emphasize. I want to emphasize that some of the projects. So because this quantum is a best applying qubits, so we are doing some quantum communication stuff. So for instance, a quantum key distribution is one of our workhorse for the photonic quantum information team in KIST. So we have developed a QKD network. You know that quantum key distribution is usually one-to-one communication. We have developed some 1/n or n/n QKD network systems, and this has been tested to with the KT and some Hyundai. It has been tested in the field, and this technology has been transferred to some startup companies as well. Also, we are doing some twin-field QKDs for long-distance applications, as well as a continuous variable QKDs for budget demonstrations. And also, we have lots of researchers focusing on integrated quantum photonics as well. So for scalable and practical implementation. For instance, we are actually developing quantum source and manipulations, those kind of things as well, right? And then, of course, we are doing other fundamental applications using photonic qubits and more. And my talk is actually a part of some of the fundamental applications utilizing a photonic qubit. So now I can move on to this. My real topic of my talk. So let me just briefly introduce the discrete variable and consensus variable in quantum optics. So as you know, right? Quantum is very weird, and we all about the duality. So all the quantum object can be particle as well. At the same time, it can be a wave, right? Photon or the light is also can be seen as a particle as well as a wave. So it has a particle nature. At the same time, it can have a wave nature. So when we consider this particle nature of a photon, we call this as a discrete variable, because in this immeasurable, this particular number of photons, you can encode those qubits. For instance, your radiation can be a qubit, or your path or your rectangular momentum can be other. So discretized quantum systems can be some qubits or some qubits as well. And these are some of the properties about this particle discrete variable quantum optics. At the same time, you can view your light as a continuous wave, which has a x and p quadratures. So one of the things is that there's strength of a discrete variable viewpoint and weakness continuous variable viewpoint. Strength and weakness are somehow comparable. So for instance, okay, for discrete, with practical nature, this quantum state and gates are highly, and can be implemented in high fidelity, and also the photon will be, this kind of quantum state can be robust against the photon loss. However, the quantum state generation and also the gate operation should be progressed. In the meantime, however, that for the if you do a continuous variable quantum optics, you can do a state generation, also entanglement generation, and also measurement can be deterministic just by simply interfering those a photon. I mean, this is a light field and a beam splitter. However, this can be fragile to a photon loss and other frequency. So you can immediately think about, okay, why not just hybridizing those discrete particle nature and wave nature to enjoy both strengths while suppress the weakness. Of course, that if you do this badly, maybe just you can have both weaknesses rather than both strengths. However, people are doing that. So if we see the history, right? So people are doing that. We are not the only ones who are considering this discrete variable and hybrid. DB and CB hybrid systems. So more than 10 years ago, there are several implementations of DB-CB hybrid systems. So those kind of, those works are some of the examples about the DB-CB quantum teleportation and also entanglement swapping. However, most of these kind of experiments, the works has been encoded using a so-called a single layer discrete variable and continuous variable. So in a single layer discrete variable system, you actually encode your qubit into a number of photons. So if you have no photon, it is encoded, it is considered as a 0. And if you have one photon, just you can say, okay, this is the qubit 1, right? So for instance, the entangled state between DB-CB hybrid entangled state, which was generated here, was a 0 and cat state. Here 0 is the number of photons, cat plus, or the 1 and cat minus state. So this kind of thing. So of course that, this is actually very easy to implement such a DB-CB hybrid entanglement and some teleportations. However, it has some drawbacks for it. Okay, the first thing is that it is actually questionable that we can really say that this is a DB and CB hybrid entanglement because that this DB encoding has been utilized a photon number, which is actually subspace of continuous variable systems. So, and more importantly, actually, because that just you actually encode your qubit into a discrete variable qubit onto your photon number, actually this is fragile to your both of photon. So which means that you cannot really enjoy the strengths of discrete variable scenario. So people actually try to overcome this. Overcome this limit. So to try to implement so-called dual layer discrete variable and continuous variable hybrid systems. So there are only one. There has been only one experimental demonstrations about 7 years ago, like that. So here, actually, people implemented a polarization qubit and cat state entanglement. So for instance, okay, so here as you can see here, so they actually could. Here as you can see, so they could generate a horizontal photon and cat plus state and the proportional way vertical and cat minus state like that. However, the limitation of this wonderful work is actually first of all the entanglement entanglement generation was based on the coarse selection, which means that when you actually when you measure the photon, just you can be sure that okay, there was an entanglement. And secondly, this discrete variable part of photon was not really in a single photon encoding. However, if we call process, that's why that actually in your teleportation fidelity has been highly biased. As you can see, this is the teleportation fidelity. The teleportation experimental result. So here, so when you actually teleport the horizontal photons, you could achieve very good visibility. However, when you teleport the vertical photons, their visibility was about half. This is because that their discrete variable photon, which is a photon, was not actually was not really a single photon, but the we call it process. So our research project is to overcome this kind of things, right? So at the moment, so the KIST and ASTA in Singapore and Australian National University in Australia, we are now conducting an international collaboration research project, which began last year October. So it's about year since we began our research project, and annual budget was about 1 billion Korea won, and part of the money goes actually to directly goes to Singapore and Australia. So our goal is to develop a dual DBCB hybrid quantum optical information processing, and so we actually want to develop discrete state television CAST, CAST state whatever, and dual DBCB quantum teleportation as well. So our team is like that. So in KIST, so I myself I'm doing a quantum optics experiment. So I'm doing this one, and we do have some theory team led by Dr. J. So he is doing DBCB hybrid quantum network protocols as well as some theory works. And we are doing so we also have a team on integral quantum photonics. So Dr. Kwon is leading the integral quantum photonics team, who is developing a integral quantum photonics based on discrete light sources. So we want to replace our OPO to a single pass OPA eventually. Our collaboration our international collaboration team is led by Professor Pinko Lam, who actually used to be a ANU, and now actually he has jointly so he actually recently moved to A-Star, and somehow he has a relation with ANU and A-Star as well. And among them, so for A-Star part, Dr. Young Jo is leading the group, and in ANU, Dr. Sophie Jie Zhao is leading the group, and so just we're tightly collaborating. Because that in KIST we have a strong background in discrete variable quantum optics experiment, and in the meantime, Pinko Lam's group has a strong in continuous variable quantum optics. This is a collaboration with extension. So I don't really have much time right before.
We have plenty of time.
Oh, we have plenty of time. Okay, so okay, so I see. Thank you. So because it's been only about a year, we don't really have much progress. However, we already had some we could bring some idea to implement a DBCB hybrid entanglement. For instance, okay, so in this scenario, we actually have proposed. We are proposing because we are writing a paper though. So we are proposing a entanglement generation scheme. So which is not based on heralding scheme, but not based on post-selection, but the heralding based on heralding. So here we have a type 2 SPDC, so which is typical way to generate just single photons, herald single photons. And here's the wave squeezers. By interfering them at a beam splitter and have a click, photon click, either this detector or that detector, actually we figured out that we can generate a horizontal cap flow state or vertical cap, this is polarization qubit and a cap plus or K minus state in DBCB hybrid entanglement. So this is, some of the, so when we actually project our horizontal photons to, our discrete variable, DB signal photons to horizontal, vertical, or diagonal anti-diagonal state. So this is some regional function, the phasor diagram of a CB state, and we actually found that this is, the overall fidelity is over 99%. And we also have investigated the effectiveness of loss, and even with the loss, our protocol seems to be quite lost. And to utilize this kind of a DB-CB hybrid entanglement, we are actually designing a DB to CB quantum teleportation. So here we can generate the DB-CB hybrid entanglement, and then we have another photon, a single photon here. So as we want to teleport this quantum state to this CB state, and this is going. So this part is to verify if the CB state is actually well teleported based on this one. So our theoretical analysis shows that even with some loss, so affordable loss, like a efficiency of channel efficiency of 0.85, the average fidelity can be achieved. We can achieve the average fidelity over 99%. So 99%. First, we are investigating the CB to DB quantum teleportation, which means that here the DB to CB entanglement, and we actually have another some CB input, right? So some arbitrarily K plus or K minus state superposition state, and when we do some penalty measurement, like a so-called entanglement measurement in CB state, we can teleport the CB state to this discrete variable system, right? And the overall average fidelity could be higher than 98%. Of course, we have no idea how to implement such a complicated K plus and K minus superposition state, but still, at least in theory, we can verify that our resource state, the DB-CB hybrid entanglement, is quite good enough to explore. Lastly, just we are also developing our CB kind of optical experimental skills here, because basically that just in KIST we have been done a discrete variable kind of optics. We didn't really have much experience on CB. So with the help of ANU and A-Star, just we are developing for instance, a squeezer. So this is the squeezing setups in my laboratory. So this year we could achieve about 3.5 dB of squeezing, and we wanted to develop this a lot better. However, our laser has been died. So recently, we got back our laser from Denmark, and now we restore our setup, and we still could achieve about 4 dB of squeezing, and we are developing furthermore. Yeah. So to summarize, actually, maybe the DBCB hybrid or whatever, this kind of scientific contents may not be really important though. So we are actually happy to invite possible collaborators and just believe that we have a great guest house, and so this is a great location and facilities. And via a international collaboration, we really seek for a synergy, because the KIST is strong in discrete variable optics experiment, and A-Star and ANU are strong in a continuous variable optics. We are actually aiming to develop some DBCB hybrid optical information processing, and we are actually looking for more collaborations. Before closing, I will have to thank to my sponsors, as well as my collaborators and my postdocs and students. So most of the work has been led by Dr. Dilipan and Dr. Jishan, and also Taehyung and Dr. Seokjin Kim and Minju. As you can see some of those things. And yeah. Thank you for your attention.
So this presentation is open for discussion now. Any question? I have a question. So as far as I can tell, these 3 countries international collaboration is sort of like caused by sort of human migration from KIST to Singapore.
Yeah, actually, yeah, you're right. So usually, because all of the 3 groups we are doing all experiments, right? Really tight collaboration is not really easy, right? So rather than just the human exchange, I would like to emphasize that this collaboration begins with my sabbatica in ANU. So actually, I had a sabbatica year. So I stayed in ANU for a year in 2022, like that. So during the time, during my visit, just we initiated. Of course, this project we didn't have any money to work, but we initiated our collaboration, and based on that, just we are trying to exchange our people. For instance, this year, one of my students actually has been in Singapore for 6 months, so like that. And also, we have many visitors from Singapore and in AIM.
Okay, so based on this personal exchange.
Yeah, and the personal exchange actually bring some. It can bring knowledge exchange as well, know-how and knowledge exchange.
Any other question? Then let's thank the speaker again. We'll move on to the final presentation before discussion session, before discussion time. So this talk is going to be presented by Kim Jin-hee from K-Quantum International Office of KRISS. The title of the talk is Korea's International Cooperation Strategy in Quantum Science and Technology.
Final talk in final session. It's a long day. I am the director of the K-Quantum International Corporation Office. As you may notice, is one of the sponsors of this event. There is K-Quantum logos there. And I'll briefly review the Korea's international cooperation strategy in quantum science and technology. This is my contents. First, I briefly review the Korea's international cooperation strategy, followed by the introduction of K-Quantum International Cooperation Office. And I'll give some review on some key international collaboration program ongoing, and which is followed by the international cooperation events. Here Here is some brief review of the Korea's vision in quantum science technology. The quantum science technology strategy was first announced in 2023, which is followed the Quantum Act in the next year. And Quantum Initiative was launched in 2024. And this year we make a strategic committee in the quantum science and technology. So our motto is in Quantum Initiative is quantum beyond the digital. And we hope to be a leading quantum economy by strategic international cooperation. So our government increased the capacity of the quantum investment in recent years. And because we are the latecomer in this field, we have two-step approach and comprehensive support strategy. Until 2030, we hope to be a global lead in this field, becoming a leading country in quantum science technology. And in 2035, we hope to be a key cooperation country to technological alliance. So we have to overcome the limitation of the latecomer. So we make some comprehensive support plan in this field. So this is our strategy. First, we promote the open innovation. So we extend our global joint research program. There are several programs ongoing, and we hope to participate in the global joint research programs such as Horizon Europe. And we promote the international solidarity activities like the QDG and MDQ. And we hope to respond to technology control and supply chain. And to support these the activities, we built the International Cooperation Organization. We made the Korea-United States Cooperation Center in 2022 and Korea EU Center in 2023. And previous year we launch the K Quantum International Cooperation Office, which is the hub of the international cooperation in the field of quantum science and technology. So these are the core missions of the K Quantum International Cooperation Office. We are planning the international cooperation strategy with the help of the Ministry of Science and ICT. And we also make the Global Joint Research Program with the help of the National Research Foundation in Korea. And we do promote the activities for networking hub. So we arrange many international meetings and conferences, including Quantum Korea. And we make the many research network worldwide. We also have the talent exchange program, both in academia and in industry. And we have the academia industry to be globalized. So to achieve our goals, we co-work with many institutes and organizations. For example, the funding agency like the National Research Foundation or NIA and IITP. Also, we closely work with the Ministry of Science and ICT. Also, we work with the international standard organizations such as ISO, IEC, and BIPM. And we have two the overseas centers. One is in the United States, one in Europe. And we are the K Quantum International Cooperation Office, also in charge of the Asia Pacific region. That's why I am here. I briefly review the several ongoing projects in the international collaboration program. First one is the Global Joint Research Laboratory. This is focused on the fundamental research and also include the early stage product testing and validation. Now there are 13 laboratories worldwide, and the 4 more will be added this year. among them four, there is one institute presented by Yong-Soo Kim. This is the Global Joint Research Laboratory, launched this year. And there is a bilateral joint research program which is based on the MOU between the funding agencies in both countries. We have now two programs. One is with Switzerland, one with the United States. And we hope to add more programs and projects in this field. And there is a Quantum Global Partnership Program, which is a university center, a contract-based international collaboration program. One of them is the presented by Eun-Sung Kim, KIST and MIT. This year, the two programs is launched this year. Our organization also arranged many international cooperation events. Some of them are listed here. First of all is Quantum Connect in April. And we also organized many international cooperation programs in Quantum Korea, round table, and seminar, and so on. And we hope to make a quantum dialogue in this at the end of this year. In Quantum Korea 2025, there are more than 4,000 participants, including visitors. And there are many programs, special lectures, academic sessions, and industry exhibition, and networking and other events. So that's my presentation. So you think this? You can think this is a K-Quantum International Cooperation Office is a kind of national contact point in quantum technology. So if you have something to collaborate with Korea, you can contact anytime. Thank you very much.
Okay, thank you very much. Any question about this presentation? I think you mentioned that K-Quantum is the center, connecting point for quantum technology, but totally excluded from science.
Quantum science and
Science and engineering. Any further question? Then let's thank the speaker again. And let us move on to our last event where we'll have some discussion before lunch. Okay. So please join the discussion. Discount that we have selected is Michael Brenner from University of Sydney, General Report RMIT University. Alessandro Solin, himself, Gavin Brennan from Victoria University, Sung Lee from Postgrad, and Yong-Soo Kim from KIST, also J.D. Kim from KRISS. If I just say like let us discuss, then so I made some silly questions to start with. Because this discussion is also open for the floor, so if anyone interested in what are these questions? Okay. That's why I'll do I was thinking two questions that I have in my usual silly, but quantum technology is the future, people say. What is that quantum and when is that future? Okay, that's the first question that I have. Okay, But you may also say like we are predict probabilistically this. Okay, quantum vocabularies are not allowed. Okay, no probabilistic or no probability or no superposition or like not determined or something like no. Classical answers are allowed. Okay? So the question is this. Okay, question number one, I think quantum technology is blank. And question number two is, I think the future is blank. Okay? Anybody? Start. Let's just start.
So from my perspective, I mean, we often talk about generation 1 and generation 2 of quantum technology. So we have lasers, we have MRI machines. Quantum mechanics is necessary for many things that we use. So when we talk about quantum technology, we have to be a bit more subtle. It's about processing information using the laws of quantum physics. Because conventional computers can be described as classical information. Even if the components still use quantum physics, the information is still being processed in a classical way. So this is how I usually make the distinction. Whether it's a quantum computer, or quantum communication, or a quantum sensor, you're processing the information using superposition or entanglement, something quantum mechanical. So that's why I would, and most of us in this room know that is much more different because quantum information is much more fragile, and that's why the technology is different to what we already have. That's why we have to think about the atomic scale. That's why we have to think about very cold, very high levels of vacuum, anything like that. So all these technological challenges come from that restriction. When is, it depends on whether you're talking to government, scientists, or people writing checks.
So it depends on measurement.
I wasn't allowed to use quantum topics. So there are literally sensors that use superposition states in field trials now, in aeroplanes, in boats. So sensing is now. Is there a product on the market that you can buy which is significantly better because of that superposition? I would probably say no. I think we don't yet have sensors that are that much better than their classical counterparts that you would choose between.
Anybody else? Challenge, particularly.
Yeah, the problem.
Yeah, I guess I would probably add that this also quantum technology like 1.5, so stuff that uses things like entanglement or countable numbers of photons, but it's a technology that already work. So quantum key distribution would be an example. You can buy systems right now, and they offer security beyond the level of classical security, and also it's like future-proof. And then in sensing, there are also sensors that just depend on having two photons in the middle of entanglement, don't necessarily require cryogenic temperatures, don't necessarily require going to like very large number of quantum bits for processing like large sophisticated quantum states. So we are currently in this like intermediate range where real quantum effects start playing a role in technologies that are like right now or will soon be available on the market, even before big quantum computers become available.
Quantum technology, I think, is inevitable. If you consider the semiconductor technology, I think, I guess it takes about millions of electrons to store a single bit of information. But it easily become less and less. So if you shrink the structure of the memory cell, then you can reach the quantum region. This because it is an inevitable pathway. But how can we reach the region? It depends on the level of the questions. Is there the feasible technology, or is there some technology can make a big revenue with the quantum? I think it takes more than 10 years, but the quantum technology is an inevitable pathway, but how long it takes, it depends on.
So it depends on the measurement. Anybody else?
I think quantum technology is a problem, many problems to solve every year, because in my opinion that we have many problems, but so we have some solutions for that, but after all we find another problems to solve, so maybe we should have many things to solve in the future. So I think quantum technology is the problem we need to solve in the future. And the future that I think is that I'm a theoretician that I'm currently taking care of some error problems. So I think due to the severe error problems, I think it takes more than expectation. So
maybe just I can add following Sunu, who is a theoreticians. So as an experimentalist, I would say the quantum technology is maybe in the laboratory. so always the theoreticians actually define a new problems, and experimentalists try to solve the problems. And of course, that the theorists actually prove that okay, their solution was incorrect. So it's kind of, to me, it seems to be like a kind of a race between theoreticians and experimentalists. So which is a productive way of the race between those. Maybe that's why the collaborations, international collaborations as well as the theoretical experimental collaborations would be important. So when it would be available, so actually I strongly agree with the opinion that QKD, for instance, or some of the quantum centers are already available in the market, even in the market. So only problem always QKD would be the advantage of QKD can offer is quite tiny with respect to the cost, right? So just to be maybe either we can down the cost, or just maybe we can make a benefit larger. So this would be one way we have to think about. Maybe that's why the continuous variable QKD is interesting as well. But okay, so somehow maybe that's assuming that okay, most of us are interested in when a quantum computer would be available. I would say that okay, when these experimentalists win the theoreticians, and that's when this quantum computer will be available.
So what do I think quantum technology is? It's a challenge, and I think this is where it's going to be for some time. And it's an interesting challenge because we're seeing at the moment, as someone who's been in the field now for like 25 years, it's been really fascinating to see the evolution of this going from the way I'm a quantum algorithms and complexity theorist. The way I used to describe my work to my friends would be, I work on developing algorithms for computers that are probably never going to exist. That was my job, and it was a thing that you did at the university. And now my job is working with multinational companies to try and work out how to improve application flows for models that have been struggling with for 50 years in some cases, right? And so, yeah, it's a challenge that we're dealing with, and it involves a lot of different moving parts. Again, also seems to the way our jobs have evolved, in that it used to be I would talk to some students, me being a student, and talking to the postdocs and my friends at the conference. And now it's we're talking to people across a broad range of fields all day, every day. And that's it's a broad challenge for the whole world to progress. And when is it? I don't know. Tomorrow? No. Clearly it's a ways off.
Yeah, so maybe just to pivot a little bit about that, just thinking about use cases for quantum technology, particularly quantum computers. Like, we spend a lot of time, by we I mean like people who work on algorithms and quantum computing in general, of thinking, how much faster is quantum algorithm going to be versus the classical algorithm? But I think we're not anticipating the new kinds of problems we're going to develop once we have quantum computers. Like before classical computers, there was not public key cryptography like we have now. Like no one was thinking about using elliptic curves for encoding information. People weren't thinking about chaos theory. I mean, there were some theoretical models, but it didn't become an empirical science until we had big classical computers. There's no way you would be able to simulate it. So I think once we have these things, there's going to be a whole bunch of new problems that we're going to find extraordinary speedups, or just problems that have no classical analog. And we're going to see like a whole new areas in science develop from that. I mean, some of it, of course, will have applications for like advanced materials design in chemistry, but there might be whole new kinds of problems that involve game theory and machine learning intrinsically that have like subroutines that are quantum, but are buried inside of a larger classical processing. And when that's going to happen, I don't know, but I am fairly confident by the early 2030s we're going to have something useful in a quantum computer that's all-time.
Something useful, which is challenging, which is what you said. You said something. You described quantum was what? Inevitable. Future can be like 30 years. This is useful is 5,000. Okay, so I will just open for further discussions while we are having or people in the audience. Any your idea to share with us? Yes.
I guess listening to the presentations today, in some sense, it seems like it's driven by the investigators. The scientists are doing what they're interested in, and that's merit. Other countries seem to have a very deliberate, strategic approach. Is there any sort of best practice that countries could adopt based on what we've heard today? That's the question.
Good question?
Yeah.
You're not supposed to answer these questions.
Oh. Sorry.
No further questions are allowed.
Sorry. I'm not going to answer that anyway. That was a great question. I'll just take over. It's fine. It's happened before. What's really interesting, and I want to pick up on something that Mick said, was that our job has changed. So something that I never anticipated. I was offered a job in our major telecommunications company to work in the research lab, and I turned it down to do a PhD. And I did that because I wanted to work in a dusty corner of academia on interesting problems. The chief scientist of Victoria, my state, has my personal phone number. That I still find really weird. We all know many politicians now who are interested in this space. We meet them all the time. That would not have happened if I had just stayed in my dusty corner, and it would not have happened in quantum physics in the 80s. So there is this, you say, led by the investigators versus top-down. At least the experience in Australia is it's both. It was the investigators getting in the ear of the people. And Kathy Foley was an amazing push for this because she is a researcher. She still talks like a researcher, even though she's now been a pseudo-politician for almost 10 years. It has to go both directions. You have to be talking up to the people who make the decisions, but then helping the people make the decisions to invest properly or to focus properly. And it doesn't necessarily mean getting them to write big checks. Scientists tend to think of government as a source of money, but that, in a lot of cases in Australia, that wasn't actually the primary thing. It was government saying, this is something we care about, and everyone else responds to that signal. And so I think you really have to have from the bottom up and the top down, and think of it as an ecosystem. There are definitely, so you've serious points that there's a lot of quantum going on in Australia. There are very famous, very well-known Australians in quantum technology, and I listen to them talk and think, oh, God, they're just saying things that I completely disagree with as a scientist. None of them are here, so it's okay. But that is still then building up the ecosystem. And people are allowed to have different opinions on the technical level, as long as we're clear that we're trying to build an entirely new industry. There is no one solution. We're just sort of working as much as we can to build an entirely new industry. And that's really exciting, but it means that there are going to be many ways to do this, and everyone's country will have to have a slightly different approach, because there's different constraints, there's different. One of the famous things from Australia is it's really good if you can promise something in 3 years, because the Prime Minister will still be the Prime Minister in 3 years. Don't bother promising something in 10, because the Prime Minister won't be the Prime Minister in 10 years. Yeah, that's not the same in every country. There are different constraints.
I think my opinion is that we don't know there are best solution or plan, but I think we need as many plans as possible at this very moment. Yeah. That's why we are sharing this.
Now I am very envy of the Switzerland and Netherlands and Finland. They make the revenue in the quantum-enabled technology. With quantum-enabled technology, the Finland sold a lot of the knowledge of which worldwide. So I think the ecosystem of the quantum-enabled technology is very important. There are many advantages. If we have some the diverse ecosystem, cryogenics or microwave or something others, it will be very helpful. In this respect, many European countries have some advantage. But in Korea, we have a very weak ecosystem, quantum-enabled ecosystem. That's very weak.
I wouldn't worry too much about that. Don't forget Nokia in Finland, and now Samsung sells a lot more phones than Nokia does. There is still time.
Yeah, I think so. We'll leave some room for further discussion during the dinner, right? So let us move on to the next one. Particularly, this session was for international collaboration. So through quantum collaboration, we want to give and take what with each other. That's my question. So particularly, like I here means like we are here as a representative of each economy. So our economy wants particularly contribute what, and our economy wants to receive or get benefit from what. That's my silly question or not silly question. Anybody challenge?
Thanks for being on the chart. All right, so I'm going to answer this question in 2 ways. I'm going to start with myself. So for international collaboration, what I'm looking for to give is, I don't even think about how I give it. What I want to give is, the best of my abilities in, an interesting project. Because that's what I do in every project. It's like try and, here's an interesting problem, I want to tackle it, and I want to, give my all to try and work with that, work with the teammates on that. What I want to get is people who are bringing me new skill sets and ideas. Right? That's what you're looking for in any collaboration. And you want to also get people who you can be friends with and work well with and maintain, an ongoing collaboration. That's really, really, really important. I think all the collaboration we've had internationally is the ones where, we're all working together and we all knew what the goal was and we went for it together. That's always what you want. And I think at a national level, it's a little bit of a similar thing. I mean, I'm not a politician, so maybe they might think about it differently. But I think what a lot of the countries here are looking for, and discussions we've had over this week and many other discussions, it's about trying to work out how your country can get the most out of an international engagement and working together. So, when I think about the advantage strengths Australia has, we have a lot of really good quantum researchers, and that's come about through, I was asked this question earlier this week by someone, and it came about by accident. in part, and then some really good planning in part. And what we don't have though is a great manufacturing sector. And it's the thing our country is trying to address. And not to address that, we need to work with international partners to work out how to address that. Because we need to learn from the lessons that they've been through, and also to leverage their expertise to help us, improve our manufacturing sector. This is the kind of thing that you've got to think through, I guess.
Well, I'm not an economist. However, people say that by trading, just you can. I mean, the trading is not zero-sum game, right? So just you can. Both countries can have a benefit from the trading. So I think that this international collaboration should be similar to just trading. So if you consider this, we sometimes just when we do some collaboration, just we sometimes want to hide my know-how, but just better to just have some their know-how. But I mean, in this sense, actually, that I don't know that this is a proper answer though. I think that we have to think about that this a kind of collaboration, this kind of like a trading, so it is not a zero-sum game, but just we can take both benefits right then. And so we just realizing this thing should be important, and maybe that's
Good point. Trade, making the cost low, and sell your expensive ones and buy something which is cheap. Good. Anybody?
Yeah, just, one thing certainly we're seeing more in our field is security issues, export controls. So if nations who are friendly now, nations, representatives from many of the Asian countries here today, we're friendly. I hope it stays that way. There is a risk that quantum technologies will become balkanized. There's certainly, obviously, a race between the US and China. And it affects us, particularly in universities, from just having access to students and postdocs. There are some nationalities we just cannot reasonably expect them to get visas to come. So, if we can, at least between nation states, keep friendly with human exchange, students, but also senior researchers, like having programs with long visitor programs. Particularly, Australia is just far away, New Zealand is far away from a lot of other countries. It's not like Europe where you can just take a train easily. It's more of a commitment. So it's nicer if you can stay a longer period of time. These things, in the end, don't really cost that much, but have huge payoff. So yeah, I hope we can continue to foster that, and then we learn from each other what works and maybe what doesn't.
I think you have a good point. Our APEC meeting is not for fighting against each other. We are under the condition is like whatever we can, we are allowed to exchange or something. What to exchange, what not to still, that is a different question. But as long as that is allowed, how do we do that?
Yeah, I think the international collaboration is very important in many countries because the one aspect is the risk management. Those single country can afford a huge amount of investment. There are many modalities in quantum computing. So I think the collaboration is good for the reduce the risk to the investment of nationwide. So in that respect, I think the two nations, China and the US, can afford the huge investment.
They don't talk about Vancouver here.
But other countries need to collaboration with other countries. That's one point. Another one is we need more foundation in quantum technology. We have a shortage of the talent and So we, through the international collaboration, we can do some the talent exchange. That's very important. So if some people come to Korea and he get PhD and return to the Thailand, then he can do the expand his labs in Thailand. So the quantum technology foundation is extended through the process. So I think we strengthen the international collaboration.
Yes.
Thank you. So thanks for the panel discussion. I guess a comment related to one of the points Mick brought up as well. So in Australia, we talk about having a future made in Australia as a governmental priority, and we look to countries like Korea for the success in establishing such a large-scale manufacturing industry here. What lessons do you think from that process are still relevant for countries now looking to develop industry in the quantum area? For example, how should universities, research organisations, government, the commercial sector, how do they have to work together to really see the industry grow to the sort of scale that might be possible?
That's a good question. The strength of Korean Korea is the industry, especially manufacturing. But I think it's the kind of the accidental achievement, I guess, because in many countries like the United States and the UK has in some period the strong manufacturing companies in their nation, but most of the companies move out the China or the other side. But our country has not yet in the position of the national income, in the sense of national income. So the people are aware that the importance of the manufacturing ecosystem is very important nationwide, but I think the quantum technology has the same respect. Is very important to keep in this country. That's why we worry about the brain drainage. So very well-trained PhD students go to outside because there is no sufficient reward to their work. So our government is very aware of how can we stop the brain drainage. So it's a very difficult question to answer, but keeping the manufacturing in this region is very important, even in quantum technology. So and the rewarding to the well-trained workforce is a key factor, I guess.
Yes, thank you very much for the answer. But I think the Korean panel, including me, are not expert on that. I think Jui Lee, she's an expert in policy. So the question here was, in semiconductor industry is kind of success story in Korea. What was the strategy? Can you answer that? Can you comment something on that? I think, like I said, it could have been accidental, but so we don't know what caused the real reason. But and it was the reason. Was the result. So, but to me, although one thing which we worry and which we hope is it reshaped. So semiconductor reshaped our industry and our nation, particularly in Taiwan as well. But Many people think that quantum has also the potential to reshape. Like from some representative from Vietnam also mentioned that the narrow gap of reshaping computer. Maybe there are some big potential, but we don't know what quantum is. I think she will answer that while we are having dinner.
Yeah, I heard there are two steps. One is the outsourcing, and the second one is offshoring. The manufacturing ecosystem first has some outsourcing to the less important part to companies, and then move to the abroad, like Apple. But Korea is in the stage of the outsourcing, not offshoring. So that's very accidental because we are the GDP level of 50,000 or something. If we the GDP per the people was exceed 5,000, we may have also offshoring of the manufacturing ecosystem. I guess.
I think we discussed enough to discuss further while having dinner. So let's thank all the discussants and also the people in the audience who participate in discussion together. Then we will meet at 6:20 at the hotel lobby for the dinner. The bus to take the bus to dinner. But before that, let's take all the speakers and attendants to take a photo here. No photo, no dinner. Okay? Come here. Please come up, all the people, please come. Maynardo, please come here. So we'll take two photos. Kimchi photo, another one is quantum 10,000 years. Long live the quantum 10,000 years. So if you do it improperly, it's like a surrender pose. Excited to 10,000 years. 김치 해주세요.
네, ready, 김치, 1, 2, 김치. Again, 1, 2, 김치. One more time, 1, 2, 김치.
아 잠깐만, 만세 포즈로 한번 같이 하는 거예요. 10,000 years.
Ready, 1, 2. Again, 1, 2.
네, 감사합니다.
네, 감사합니다.
6:20 at the lobby. Okay? So anybody here who wanna come in? So I will count.
Stand still.
We're all invited for dinner.
시간을